We can start. Thank you.
Good afternoon, everyone, and greetings from London. So I'm extremely delighted to have you join this DSM Network Plus event. For those who are new to this DSM Network Plus, I want to say that this is an outcome of a nationally funded awarded project given by the Funding Council of the UK EPSRC, which is led by Professor Alan Matthews from University of Manchester, supported by Professor Ash Tiwari from University of Sheffield, Professor Adrian Murphy from Queen's University Belfast, and myself from London South Bank University. The aim of this project has been to bring together various communities working in the area of digitalized surface manufacturing and to help grow this area. As an integral part of this project and en route to the wonderful journey of this project, we are delivering this event to discuss an imminent issue of climate change. This is an open event for anybody to join and free of charge, of cost. And the speakers today will all be early career researchers who would be wanting and willing to present their thoughts and ideas as to how can the newly developing technologies can help to tackle the issue of climate change. It is only timely for the DSM community to bring this event up as an effort to help align itself to prepare the UK to host for the UN COP26 summit, which will take place later this year in Glasgow. So an important question we should all be asking ourselves today is why should we be worried about this DSM or rather about this issue of climate change? And to address this issue, I'm going to share my slides now, which will then help me communicate my thoughts swiftly. So here my screen sharing is. So I am the ECR lead for the DSM Network Plus, and therefore I'm going to start this event by presenting the overview of the issue of climate change. So here on this slide, what we are basically seeing in front of us is the landscape of icebergs around the planet that we have. And this is shown on the left side. And so what we can see here already that majority of the Earth, especially around Greenland, Iceland, and Himalayan regions in Asia, are covered by heavy glaciers. And surprisingly, each year, an increase in 1 degree of temperature caused by the various activities that we do, which includes emissions of carbon, particularly from manufacturing, transportation, and so on and so forth. There's a high risk that these glaciers are starting to melt. And what we want not to do is to not get to a point where there is a point of no return. We do not want to have the glaciers melted so that we are in a situation where the half of the Earth will be sink in water. And this is what is shown in the right side slide here. So what we see here is that most of the Earth would be sinked because of the glacial meltings around this region and around this region and also around this region. And as a direct consequence of this, what will happen is not only the sinking of Earth will cause 45% of the clean water availability to vanish because of the scarcity of clean water, but also it is speculated that there's a gas called DDT, which is buried under Himalayan glaciers. And the accidental release of this DDT gas will also double the emissions that we are already currently witnessing. So as a direct consequence of the glacier melting, we will have 45% scarcity of clean water, coupled together with the problem that almost the same number of people will go homeless because of the unavailability of clean earth. And that is why not only us, but everybody who is sharing this habitual planet is needed to think about this issue of climate change and need to act now before we come to that critical point. To just give you an idea, here is a Landsat image taken by NASA's organization in the US, which shows the Colombian glacier. So as you can see over the year from 1986 to 2009, this window has started to move up. So this part, which used to be earlier habitable, has now already been taken over by the water as a consequence of the glacier melting. So, and it is continue to going to climb up in the time to come. And that's what we would like to avoid. So in order to avoid this problem, we need to work towards technologies which will help the planet to remain sustainable. And as we can see, we are commonly witnessing these terms more than ever before. instances like Californian wildfire, bushfire in Australia, storms, tsunami in Japan, floods at an increasingly faster rate than ever before. And this, of course, has to do directly with the human actions. And while the government is working in parallel with concepts like net zero manufacturing, decarbonization, and digitalization, and so on, we need to make our contributions to help create that change. And this is now high time that we work on technologies, especially on the 4 pillars of engineering systems that will make the planet more sustainable. A glimpse of this technologies has recently been covered by us in our new paper that is published in Nature Asia Materials. And we have comprehensively tried to describe there how can the innovations in design, materials, manufacturing, and processes, which are 4 pillars of engineering systems, can help make that change. So without further ado and giving this sort of preamble, I would like to just briefly say that these are our vibrant team members for giving us amazing insights into various technologies and landscape of the newly developing technologies in a very snippet manner. And all of these are early career stage researchers. They have taken this responsibility to give us an insight into various things such as energy landscape, how can nuclear fusion and nano diamond batteries, for example, can help reduce the climate change issue. Likewise, Sara would be presenting about engineering biology, and Nestor, Syed, Kartikeya will present some issues and some new insights into digitalization and artificial intelligence. We will then have a short break of 7 minutes, which will then follow this talk of Dominic and Jonathan to discuss about net zero manufacturing, followed by waste recycling. And I will then request Professor Ellen Matthews to give us a closing remarks, and any Q&A sessions will follow afterwards. So at this point, I would like to now invite Caaisha to give us an extended picture of what is COP.
Sure. Hi, good afternoon. My name is Caaisha Warsame from the University of London South Bank. I will be presenting to you the Conference of Parties 26, abbreviated as COP26. A quick background of COP. It all started back in 1995, where the first COP1 took place in Berlin. Fast forward, 26 years later, we have COP26. Why COP26? Well, prior in 2015, the COP21 took place in Paris, where every country agreed to work together to limit global warming to well below 2 degrees and aim for 1.5 degrees. And the Paris Agreement was created. However, half a decade later, although progress have been made, but the commitment laid out in Paris did not come close to limiting global warming to 1.5 degrees. And the window for achieving this is closing. Hence, this resulted for the past few weeks for developed and less developed countries to experience severe climate change. Today, we gathered to ensure this time we find an alternative solution for this matter. The objectives of COP26. First, to secure net zero and 1.5 degree climate change, which means countries to prepare with emission target nationally determined contribution, known as NDC's plan, must be done to accelerate the phase out of oil, to encourage investments in renewables, and lastly, to speed up the switch to electric vehicle, then to regulate to protect natural habitats and communities. Third, to mobilize finance, which is the promise that was made by developed countries to deliver $100 billion annually must be reached before securing global net zero. And lastly, to work together to deliver. What will happen at the UN Climate Change Conference? You must be wondering. Well, more than 190 world leaders will attend the conference in Glasgow from the 1st to the 12th of November, where the UK together with Italy will host a UN climate change conference. They will review the Paris rulebook known as the Paris Agreement. They will set out how much they have reduced their emission, and lastly, to achieve the objectives of COP26 before the end of 2030. I believe progress is impossible without change, and those who cannot change their ways cannot change anything. Thank you very much.
Thanks, Caaisha. That was interesting perspective. So let us begin the technical sessions now. So we first have Iraj with us presenting some insights on nuclear fusion.
You have my slides?
Yep, go ahead.
Hi all, I'm Iraj and I'm joining from the LSBU. I will talk about one possible solution to the energy generation issue as one of the major contributors to the climate change. Historically, near a century ago, scientists discovered the subatomic energy which exists abundantly in all matter. They suggested that hydrogen-helium fusion could be the primary source of stellar energy. Two hydrogen atoms fuse together, creating a lighter helium, and the difference in the mass is converted to energy. In the early days of research, the main motivation was to steer away from fossil fuel dependency and tap into an unlimited source of energy. However, the recent climate change emergency has shifted the attention towards using fusion for clean energy production. To create a fusion reaction on Earth, two isotopes of hydrogen, deuterium and tritium, are fused. The produced helium atom is a charged particle and its energy is recycled back to heat the plasma fuel, and leftover neutron reacts with the added lithium, reproducing tritium. So technically only deuterium, that is plentiful in seawater, and lithium in small quantities are consumed fuels. It has been estimated that a bathtub filled with seawater and the lithium used in one laptop battery can sustain a modern lifestyle of one person for 120 years. It is a remarkable energy density for when the fusion reactors become operational. On Earth, we need to reach at least 10 times higher temperatures than the core of the sun to make up for the effect that sun's gravity has on this process. One developed method is called magnetic confinement. Tokamak, the main design for this technique, is a torus-shaped coils of superconductors creating a strong magnetic field which confines and insulates the plasma. Another method is known as inertial confinement, where a number of high-power laser beams are targeting the fuel cell at the same time to ignite the mixture. Many years of research has given us the recipe for a successful fusion reactor. Its physics has been around for a long time, and nowadays it is an engineering problem to fine-tune the device. To justify the construction and maintenance cost during its lifetime, a fusion reactor should produce at least a Q factor of 10, and it must be large enough to generate a reasonable amount of energy. Now, can we actually do this? The answer is yes, it is plausible. However, the closest we have come so far is by Joint European Torus, also known as Jet Tokamak Fusion Reactor in the UK. It has successfully produced 10 megawatts of power with a Q factor of less than 1 in mid-90s. The climate change is a global issue, and so is its solution. In 2006, 35 countries with diverse political ambitions have jointly signed an agreement to collaborate in what's known as the largest and the most expensive scientific experiment to this day, called Project ITER. This is only to prove the concept by reaching the expected Q factor of 10. It will also allow us to test tritium breeding and assess the safety requirements. Some of the main benefits of fusion reactors are listed here. One overlooked fact is that this field has been advancing rapidly. This graph is comparing the growth of computing power, known as Moore's law, and fusion power production until mid-90s. For a very general understanding of the constraints of building fusion reactors, if you look at these formally, they represent a relationship between the linear size of the reactor and the magnetic field intensity to the produced energy. For a while, we were at the limits of all the contributing factors, and to increase the gain, the only option was to increase the size of the reactor, hence the Project ITER. However, with the recent advancements in material science, more specifically Repco superconductors, we can reach much higher magnetic field intensities with almost no degradation, and therefore significantly reduce the reactor size while producing the same levels of output. Although it has not been mentioned in the document published by the UK government in this occasion, the findings expected from the funded research towards engineering modular fusion reactors are transferable to the upcoming fusion-based reactors. To conclude this presentation, nuclear fusion is clean and safe and will hopefully power our Earth and beyond in the near future, and will help us in not destroying our planet. Thank you for your attention.
Thanks, Iraj. From the wonderful technology, let's move on to a technology which will help generate the energy, but by tackling the waste that will come from the nuclear processes. So, Ali, do you?
Thank you, everyone. I'm Sara, and I guess am I sharing my screen, right?
Yeah, go ahead.
Great. Okay. Hello, everyone. My name is Ali. I'm a first-year PSU student from Cranfield and LSBU. My research is about the improvement of friction materials in land review systems of aircraft by the means of computer simulations, focusing on carbon-based composite materials. I believe just going through the summary of the IPCC report would make anyone worried and feeling despondent for the future of our planet. It's a 38 pages report, and the phrase "very luckily" is repeated over 40 times through your reading. So it cannot be more clear that something is real, and the clearest points here are about the responsibility of us for the climate change. Action is the antidote to anxiety and despair. But the problem is, what kind of action should be that? Firstly, we know that we have the inherent goodness to turn the situation around, and we would do that because we deeply care about our planet. Secondly, the IPCC report itself confirms that the target of 1.5 Celsius warming limits from the Paris Agreement is not really lost, and with a strong global action, we still can achieve it. At least if we act fast from today, we can avoid the worst of it. One of the solutions here can be supporting the new innovative concepts and investments in scientific approaches by being part of this society. So I'm going to briefly talk about the concept of nanodiamond batteries and its impact, focusing on the company called NDB, which I have worked with them at a very early stage of their project. We know nuclear power is one of the most power-rich and clean energy sources, but it produces nuclear waste, which needs to be stored safely, costing over 100 billions of US dollars globally. So NDB started with the question that how we can recycle the nuclear waste into something good. A big portion of this waste is radioactive graphite, which contains carbon-14, a beta ray emitting carbon radioisotope that can turn into harmless nitrogen, antineutrino, and an energetic electron. At NDB, they managed to harness the energy by turning the graphite into a C14 diamond and producing a shower of electrons inside the nanodiamonds. And in order to prevent the radiation leaks, the C14 diamonds are actually coated with synthetic diamonds, meaning that the nanodiamond battery is a safe product that bleeds electricity from recycled waste. According to the co-founder of the NDB, this product has two different merits. One is that it uses nuclear waste and converts it into something good. Second is that it runs for a much longer time than the current batteries. The concept of diamond batteries has been out there for so many years, and in fact, there have been some prototypes of the first generation of these batteries in some Eastern countries, but low power generation had limited their usage. However, the new concept of NDB has significantly improved this amount of energy on the cost of reducing the life cycle to few decades, between 12 to 30 years, depending on the purpose of their use. So NDB is green as it has no emission. It is inert to the environment and does not require cobalt mining. So it has the potential to replace energy sources such as oil and lithium batteries. So by reducing their negative environmental impacts caused by emission and toxic metal waste products. Therefore, the added values here can be the lack of harmful byproducts and also recycling of nuclear waste. Briefing the application of NDB, we can consider electric vehicle, and as they are heavily promoted by various governments. In aerospace and aviation, you can think of so many devices, especially where we need low power but continuous reliable source of energy. It can be the broadcasting equipment of a spacecraft or station, or just the black box of a typical civil aircraft. And also we have drones, which can be equipped with NDB, so they can carry out their mission with no concern on energy shortage. At the moment, I believe they are working on a project with Airbus, but I'm not sure about the details of that project. Another important application of NDB is in medical technology and devices, where recharging is a hassle. And also you can think of sensitive IT system, computers, data centers, and any other electronic devices, such as your phone, tablets, watches, and etc. That's all from me today, and thank you very much.
Thank you so much, Ali. How wonderful these two technologies are presented by Iraj and you. Wonderful. So while we continue to worry about energy and these solutions can be adapted in time to come to roll out these technologies in the market, we cannot neglect the issues that are at hand also from the biological side. So I'm now going to invite Sara to present her perspective as to how engineering biology would change the fate for us to not only combat the issue of climate change, but also to tackle future pandemics.
Hi, I'm Sara, and I'm a CDT PhD student based at Cranfield University. I'm working under the supervision of Dr. Saurabh Goel and Dr. Kumar, and I'm here to talk to you about engineering biology and how it can help us address one of the most threatening impacts of climate change. Our planet's carbon cycle is out of balance, but that's not our only problem. We are all familiar with climate change and it being predominantly a result of CO2 emissions and CO2 accumulating in the atmosphere and inducing global rising temperatures. We are even witnessing the consequences firsthand through extreme weather events all over the globe. Such a big planetary change also threatens oxygen availability, as global oxygen levels have been on a steady decline. The projected changes in weather patterns and climate will also reduce water availability and affect water distribution. And this will lead a projected 2 billion people to resort to the use of unsanitary water resources. These three factors will create a certain thermodynamic state that will be a host for a diversity of dangerous pathogens, unheard of as of yet. We're already witnessing the rise of superbugs through the emergence and spread of antimicrobial resistant pathogens. Now, what is antimicrobial resistance? Put in simple terms, antimicrobial resistance is when microbes no longer respond to any drugs that are used to treat them. This resistance occurs naturally but slowly. However, due to a variety of factors, one of the main drivers being climate change, this resistance and resistant infection transmission is heavily accelerated, and new drug innovation is lagging behind. So AMR is a threat to global health, to food security, and to development. And if it is not mitigated in the near future, it is projected to kill around 10 million people per year by 2050 worldwide. Mitigating AMR has many levels to it, and it all starts from the responsible personal use of antimicrobials. And it goes all the way to governmental, national, and international responsibilities, specifically in supporting research in promising areas. One of these areas that is and will continue presenting very high impact pathways and innovations with regards to engineering combating AMR is engineering biology. Engineering biology is the innovative interface between engineering and biology, and it has already contributed heavily to the advancement of healthcare and healthcare research. Some examples of the development of these developments are development of biomedical implants and patient-specific biomedical implants, microneedles, which have a variety of applications, including disease diagnosis and treatment, an organ on a chip, where therapeutic response of organ tissues can be studied to model organ response. Generally speaking, engineering biology is built on three main pillars or research areas. First, bio-inspired design, novel materials, and bioengineered cells and systems, all of which could be exploited to tackle the problem of AMR. Combating AMR through bio-inspired design comes in the form of prevention of surface contamination and fomite spreading of microbes. The main idea is to design a surface that can either stop microbes from adhering or kill them as they do adhere. These kinds of surfaces can be used in a variety of applications, such as transport, food packaging, and also in healthcare, including for surgical tools and biomedical implants. Innovation in materials and material systems can also heavily contribute to solving the AMR problem. Few of the main areas of interest at the moment are antimicrobial peptides, antimicrobial nanoparticles, vaccines, and chitosan, which are all promising next-generation antimicrobials. A very interesting and new method that is being explored is called quorum quenching, and it makes use of specific enzymes to intercept or degrade the signals that are sent by bacteria to communicate with each other. This method does not inherently kill bacteria, but it creates the conditions for the natural host immune system to eradicate the infection before any virulence is established. Innovation bioengineering cells and systems, the third pillar of engineering biology, can boost the fight against AMR through quantitative modeling and synthetic biology. For example, by making biosynthetic gene clusters that we can use to understand and predict pathways of drug resistance, and hopefully we can then mitigate them. It can also help us through bioengineered delivery systems that would employ targeted drug delivery, which can reduce AMR significantly. To conclude, we as a species are experiencing several existential threats, with climate change being the main driver. Scientific research has a track record of getting us out of ruts like this, most recently experienced with COVID vaccine treatment and vaccine research. That is why, now more than ever, supporting and accelerating multidisciplinary scientific research should be our top priority. Thank you.
Thank you very much, Sara. That was really fascinating. So moving on from the world of engineering biology, now we can leap towards the new age of digitalization and artificial intelligence, for which a lot of researchers are working throughout the globe right now. In that space, I would like to specifically invite Nestor from University of Sheffield to share with us some perspective of digitalization.
Okay. Thanks a lot, Sara. Good afternoon, everybody. I am Nestor Sanchez, a first-year PhD student from the University of Sheffield. Today, I will cover this topic, which is the role of digital platforms in decarbonization. In the previous presentations, we have seen the drivers behind digitalization. The Paris Climate Agreement brings an economical and social transformation to decarbonize the industry to achieve net zero gas emissions by 2050. It is also understood that human driver is the major contributor of the global temperature rise in the last decade, causing the well-known environmental effects of Earth overheating. You may be thinking, what is the technology role in this scenario? How does it fit? Let's think in this word, digitalization. Digitalization is more than simple definition. It comprehends a framework which consists in infrastructure and market changes along with digital transformation, which together are linked to the decarbonization goal and to the Industry 4.0 strategy. From this perspective, the digitalization presents the following benefits. Decision-making. There is no other more valued feature for organizations than being able to take fast and accurate decisions based on real-time data. By being able to see real data, it is possible to monitor performance and track parts and products through manufacturing systems. Through the use of embedded sensors in a product, the product lifetime can be extended and tracked, monitored, and forecasted. And finally, end-of-life strategies as disassembly and recycling can be improved or created to help in the decarbonization goal set in the Climate Agreement of Paris. So, what is digitalization from a technology perspective? It is being able to represent in digital form all processes by which products are produced. Let's take a look into a digitalization example of a roll-to-roll system concept, which is being developed by the University of Sheffield. The roll-to-roll system is widely used in the flexible electronics sector and enables functional coating deposition in a roll-to-roll fashion. In this case, the output will be the coating thickness in nanometers and coating surface quality, which means free of cracks, voids, or other surface disturbance. Now, let's see some of the inputs. First, we need to understand the tension control for unwind and rewind zones. In this case, we need to calculate the roll radius to be able to calculate tension in an open loop fashion. We can use load cell sensors to measure the real tension in the system to compare calculations versus real data and convert it to a full closed loop control. The speed control is measured by an encoder sensor directly affected by the coefficient of friction of the roll and the material of the web, which can vary significantly. The input and output tension in this section also plays a role in the velocity control feedback. Depending on the vision sensor to be used, the positioning of the system affects directly to the coating scan. In this section, artificial intelligence and machine learning can be applied to recognize defect patterns. These are just examples of the input basics that must be considered to digitalize this specific system. You may wonder, what could happen if all these parameters are not understood and sensorized? We will have defects as floppy web, waviness, voids, fluttering, among other related features. By digitalizing any system, we can do in situ measurements, which will allow us to detect defects and disturbances in real time, producing less scrap and being more eco-friendly. As previously shown, we can infer that digitalization and the transition to digital platforms come with diverse challenges. Technology complexity. All systems have their own and unique complexity, either to dimensions, cost, product nature, or technology limitations. Digitalizing a system is not an easy task. Additionally, and from a wider perspective, global policies and political implications must cope with the speed and need of new strategies to do efficient implementations. Also, the value chain transformation implies cost of adaptation, which not all the companies are willing to afford. All these challenges triggers needs for further research. We must consider that digitalization has its own environmental risks, talking about its respective needs of resources and energy. This must be monitored to avoid causing a major problem during implementation. The speed of digitalization and the transition to circular economy through Europe and the world needs to be measured and understood as a whole to ensure the success of global decarbonization, and the potential to scale up and digitalize the existing architecture and technologies are an open topic for further research. Definitely, a strong collaboration among all of us is the key to success. I would like to thank you all, and please remember to keep in touch. I will now return the control to our host for Q&As.
Thank you very much, Nestor. That was really brilliant. To see how digitalization work that you're doing is going to create newer kind of flexible electronics, which is going to be a billion-dollar market. So we move on now from digitalization to the journey of artificial intelligence and machine learning, which are an integral part of digitalization. So I'd like to invite Syed to show us the new landscape in that area.
So good afternoon, everyone. My name is Syed Hussain. I'm a first year PhD student at LSBU, and my research is on CFD simulations of pathogen-laden saliva microdroplet propagation in an office environment, which has been supervised by Dr. Sara. And today I'll be talking about machine learning for sustainability and climate change. Machine learning can be used in a variety of ways to predict, monitor, and optimize human processes and the effect that we have on the planet and its ecosystem. It can be applied to many sectors, almost anything that requires digital management or that could benefit from digital management. Sectors that come easily to mind are transportation, climate prediction, and farming and forest management. But other sectors such as energy production, building management, and even geoengineering can be considered when discussing machine learning. Autonomous vehicles are also still in the infancy, yet they provide one of the most tangible effects of reducing climate change. The likes of Tesla, Optimus Ride, and Uber are heavily investing in autonomous vehicles for private and commercial use. Amongst other advantages, such as reducing the chance of road traffic collisions and an always alert driver, one of the most compelling advantages of AV is eco-driving. Vehicles that can communicate with each other, that can also accelerate and decelerate simultaneously, which would eliminate the sudden peaks of heavy acceleration and the subsequent unnecessary braking, will ultimately save fuel and reduce carbon emissions. In commercial vehicles, there is an added benefit of increased fuel efficiency by platooning. This is effectively trucks reducing their air resistance by driving incredibly close together, also accelerating and braking together. That would only be possible through autonomous vehicles. There's also automated afforestation. This is a practice of planting trees in new places, and it's also a form of long-term CO2 sequestering. And theoretically, up to 900 million hectares of tree coverage could be added globally. However, it has to be ensured that there is a positive impact when planting the trees. Afforestation at the cost of carbon sink ecosystems could result in a net increase of greenhouse gas emissions. Wide-scale afforestation requires due diligence towards the local biospheres and how new trees could affect native species and vice versa. Machine learning can also be used in automating large-scale afforestation by monitoring and examining numerous sites, looking at plant health, assessing weeds, and then selecting the optimal space and time to plant these trees. So countries like China could benefit massively from automated afforestation, as their future agricultural independence depends on their afforestation program. So next we have material science, and there is a constant endeavor to create better materials for a range of applications. However, the process itself can sometimes be slow and imprecise. The physics behind materials are not always completely understood. So often humans apply heuristic methods to understand a proposed material's physical properties. Example of a heuristic method such as trial and error can ease cognitive loading during decision making, but at the cost of either resources, time, or a combination of the two. And so machine learning can automate and accelerate this process by combining existing heuristics with experimental data, physics, and reasoning to apply and even extend existing physical knowledge. And so techniques such as supervised learning, deep learning, and generative models can be used to synthesize, characterize, model, and even design new materials, such as new solids for lithium-ion batteries, materials that can be absorbed by materials that can absorb CO2, or alternatives to cement, which, as an industry, would be the third largest CO2 emitter if it was a country behind China and the United States. So thank you very much for your time and attention, and we'll get to questions later probably.
Thanks, yeah, we'll get the Q&A at the end, but very fascinating videos, really amazing. So all of this, whether it's digitalization shown by Nestor or the use of AI by Syed, is impossible unless we have super computers or superpower computers. So moving on from the age of semiconductor-based computing, we're now set to go on to the journey of quantum computing, which will be the next topic presented by Kartikeya. So Kartikeya, please go ahead.
Is my screen visible?
Yeah, we can see.
Hello, my name is Kartikeya Parmar, and I am a first-year PhD student at LSBU, and currently I am working on nano indentation and nano sketching of diamond under Dr. Sara. And today I'm going to give a brief introduction of the applications of quantum computing and how quantum computing can help in mitigating climate change. So basically, what is quantum computing? So quantum computing employs the principles of quantum physics, and it utilizes distributed probability amplitude. So it has the potential to solve the problems which are far beyond present reach. For example, the problems related to generation and storage of power, the problems which are involved in material and technology, such as the manufacture of aeroplanes, ships, the problems in power transportation, and also the problems which are involved in the manufacture of steel manufacturing industries, cement manufacturing industries, and fertilizer manufacturing industries. So let's see some of the applications of quantum computing. Quantum computing has its application in different domains. For example, it has application in fluid dynamics and logistics. Quantum computing can improve the design and operation of equipment which are affected by fluid dynamics, especially when they are coupled with better quantum data encoding. For example, automobile makers, airplane manufacturers, they rely on CFD for the design of their products. Today, due to limited simulation capabilities offered by classical computers, they use moderate effective tools. But by the help of quantum computing, they can optimize both drag and lift, and that can help in reducing carbon emissions. Next important application of quantum computing is in the field of complex supply chain. Complex supply chain is affected by different factors such as product variation, transportation modes and routes, client constraint, and cost. And any of these factors can affect the problem of supply chain exponentially. So by the help of quantum computing, we can generate a solution to these problems. And in the next 10-20 years, different kinds of solutions which are generated by the help of complex supply chains, such as shared transportation, and that helps in saving transportation cost. Next is new materials. So the complex problems which are involved in optimization of material science can be addressed by the improvement in quantum computing. Lighter, stronger, and better insulating materials can be generated by the help of quantum computing that can reduce the carbon emissions from the buildings, aeroplanes, and also from the industries which are involved in the production of steel, fertilizer, cement, etc. Next one is carbon capture. So by the help of quantum computing, we can generate catalysts that can help in capturing carbon both at the point of source, that is at the point of generation, and also from the atmosphere. Next is ammonia. As we know that there is a huge amount of natural gas emission is there whenever ammonia is generated by a Haber-Bosch process. So in the near future, we can generate the catalyst that can generate ammonia naturally by replicating the SEMACO molecule that generate ammonia naturally. So by the help of quantum computing, we can replace the Haber-Bosch process in the next 10-20 years. And the last one is the hydrogen power. So hydrogen power, the splitting of water molecule by the help of expensive platinum can be replaced by quantum computing. Now let us see some of the energy efficiency of quantum computers. So the operating cost of quantum computers is quite low as it depends on the operating time. The operating time required by quantum computer is very less. It is around 200 seconds in comparison to a Summit supercomputer, which solves the same problem in 2.5 days. So as the operating cost depends upon the operating time, and operating time for quantum computers is quite low, so we can say that the quantum computers are energy efficient also. There are a few examples of quantum computers written on the left. They are single purpose devices. An example is D-Wave 2000Q, noisy intermediate scale quantum devices, which is a Google Sycamore quantum processor. So these are classified on the basis of algorithms they employed. In the last, I want to say that a huge amount of efforts is made worldwide for developing quantum. And in this field, different countries have spent different amount of money. Like UK has spent quantum research and development. It started it in 2 phases. In the first phase, they have created a vision for national strategy for quantum technologies, and in that phase, they have set up 4 research hubs at Birmingham, Oxford, Glasgow, and New York. And in that phase, they mostly work on the imaging, ultra-precision sensors, communication, and on the concepts of quantum computing. The second phase, which starts in 2019, and in that phase, they mostly work on the industrialization of quantum computing. Thank you.
Thank you so much, Kartikeya. A lot of new prospects coming out of quantum. You can unshare your screen. So it is amazing that we have actually managed to complete within time, which has now given us some time to do a quick question and answer session. So if anybody has questions to the speakers we had so far, we have about roughly about 9 minutes. So participants can either type their questions, which I can facilitate to spell out, or directly turn on their audio to ask questions from any of the presenters so far. So please go ahead to ask any queries you have so far. So after a break, after these questions, we will then start with the net zero manufacturing from 3:30 p.m. Of the UK time. So we have some time if anybody has questions to start with. So I'll begin by one question, Ali, I have from you. Your batteries, so their raw material is the waste, which means we need to generate that waste in order to ignite the battery?
No, thank you for the question. Basically, the raw material is the nuclear waste, which already existed, and we've got difficulties to get rid of them and dispose them. But when they use it in nanodiamond batteries, they actually subtract the graphite, C14 carbon, which is the most dangerous part of this waste, and they implant that in a nanodiamond battery. And what happens? Why the batteries itself is not going to be the dangerous waste as the nuclear waste is because they turn the graphite into C14 diamonds, and those diamonds are coated by synthetic diamonds. And as the diamonds are the most strongest materials, as you know, so the radiation leak is going to be completely shielded. So no, we don't need to generate waste. The waste is already existed, and we're going to use that and convert it into something that provides more energy out of it.
Okay, great. So Iraj, I have one question from you also. In your opinion, with the emergence of nuclear fusion, do you foresee or envision? I know it's a theoretical question, but do you foresee the drive to have nuclear fission will be at the same pace, or will it downgrade?
To be in the same rate of?
I mean, the hunt for performing and establishing more and more nuclear reactors for carrying out nuclear fission, which is the main source of energy at the moment. Would that continue at the same pace, or nuclear fusion will take over fission completely?
Okay, yeah. I think it will accelerate even more because the Project ITER is due for, it has to, they're expecting the first ignition to be on December 2025. And as soon as they, prove the concept that, it can be done, if they can produce Q factor of 10, then there will be a lot of commercial interest. It won't be only the governments to go. A lot of private companies and mainly the rich, fuel companies will invest in this technology. And obviously, as I talked about, this REPCO rare earth barium copper oxide material, they are basically a layer of 1 micron layer of material that can be very easily winded as superconductors, and they can reduce the size massively as well. And definitely it will accelerate even more as soon as they prove the concept. So far, they just, it seems like something in the distance, but as soon as they realize that it can happen, they will be,
Great. Please feel free to ask questions. I repeat again, so whoever would like to initiate any discussions with our vibrant team, please do so. In the meantime, one question to Syed. Syed, what is the issue? How do you overcome the issue of ethics with machine learning usage?
Sorry, I didn't quite catch that. How
do you overcome the problem of ethics and sometimes decision making when you have to prioritize one decision over the other? While you can have both as what you call as approach conflict. They both are positive conflicts.
It's a very good question. I haven't really thought about that. When there's two equally important decisions to be made, I think this is where.
So, for example, a vehicle is traveling, and on one side, like a road in India, you have a cow. On another side, you have a child.
Yeah.
Which side the car should hit?
I think in India it's a very different concept, because obviously cows are quite revered, and I think in that case it would depend on. That's a difficult one. I think it would depend on percentage of survivability. If you take out the cultural aspect of it, what's the likelihood of the cow surviving compared to the child, and that would depend on like the speed, the velocity of the vehicle, if the computer can actually, if the AI can observe the object that it's about to hit and kind of determine its mass, it could then identify whether it's a live object or not, and then kind of make all those decisions very, very quickly, or as it's kind of approaching the object. But it would probably be based on a multitude of not just percentage of survival, but also it could be some sort of politics as well, some sort of policy where people could say, you know what, I'm an old person, even though I've got larger mass and I'm probably likely to survive better than a young child or something like that. Don't ever go for the child, always go for me, if there's something like that kind of thing. So, it's a very nuanced.
Very, very well answered. It does not have a complete answer. I just thought to bring out your intelligence.
Yeah, it's not just, if you were to take just the mathematical approach of just percentage of survival or chances of survival, it wouldn't be, humans wouldn't really accept that. You'd have to take into account so many other factors of quality of life and all this kind of stuff as well. So yeah, it's something that needs to be intertwined with policy and human emotion or human consideration and stuff. Yeah.
Thanks a lot. If anybody has any further questions, please do raise your questions. So one question to Sara.
Yeah.
So Sara, you mentioned about engineering biology, which is a great field, and we hope that this would bring out an agility in our capability to develop new vaccines at a much faster rate, such as what we have seen for COVID pandemic. The vaccines rolled out was so fast compared to many other prevalent diseases which have not been cured fully. So with the emergence of engineering biology, do you expect that the so-called uncurable diseases would have their vaccine out soon in the market?
Yeah, I mean, definitely. developments on all levels. Like, for example, recently there has been a sort of vaccine that is being developed that is more like a pill that you can take, and the bacteria in your gut will generate that vaccine against certain diseases. So a lot of diseases that we thought we weren't be able to cure before, due to all of this new research that is being accelerated at the moment, and hopefully will continue to be accelerated even more. Definitely we will have some advancements that we didn't think we'd see.
Okay, great, Sara. Right, so time that we take a small break. So we can resume here in about 6 to 7 minutes time. So precisely it is 15:24 in my clock in the UK time. So we'll begin at 15:31 sharp. So you can leave your sessions and mute yourself, and we can resume at 15:31.